Hello everyone. In the previous lecture, we have studied about critical angle, total internal reflection, its cause, consequences, and also applications. So let's begin the next lecture and ray optics. Now till now, what we have learned is refraction through a flat spherical surface. For example, like a glass slab or boundary between water and air. So whatever we learned till now was about flat refracting surfaces. Recall the earlier lectures. The first thing we did was reflection, and in reflection we first started off with plane mirrors, and then we continued with spherical mirrors. The same light here we have done till now about plane surfaces, and now let's start with spherical surfaces. To define these, a refracting spherical surface is part of a solid transparent sphere. That is because what we get here is refraction. It should be a transparent sphere. Now based on the refracting surfaces, we have two kinds of refracting spheres called as convex spherical surface or convex refracting surface, and second type is called as concave refracting surface or concave spherical surface. Now here are diagrams of the two surfaces. The first diagram, the first one, is called as concave refracting surface. That is, there is a solid transparent medium. For example, here this whole thing here is the same medium, and also here in this case this whole thing is the medium. Examples of these are like lenses. We will see what these in the next lecture. For to understand that the interface which separates the two mediums is not flat, it is spherical. So even here the whole thing is the material. For example, think of glass. Now the question is, what is rarer, or what is concave and what is convex? Now to understand this, the name is given by that refracting surface which is facing the rarer medium. So in this case, the concave side, this is the concave side, the concave side is facing the rarer medium. Hence this kind of a spherical surface is called as concave refracting surface. In this side, the convex side, we learned this in case of spherical mirrors also. Here the convex side is facing the rarer medium, hence it is called as convex spherical surface. To understand this, there is a diagram here. For example, imagine that the refractive index here is say 1.2 and here it is 2.1. In this case, the concave side is facing the rarer medium. So for this values, this behaves like a concave refracting surface. Let's assume that this is like 1.2 and this is 1.1. So here the convex side is facing the rarer medium. So hence this, for this indices, it behaves like a convex refracting surface. So don't always go by the shape of the surface. It depends on what is rarer and what is denser, but in most cases the rarer would be outside the medium. This is what it will be, and this would be denser generally. So generally something of this shape would be concave and this would be convex. The next point is, since this spherical surface is part of a, say, since the spherical surface is part of a imaginary sphere, this would have a center of curvature also. So this point C is called as center of curvature, and this AB is called the aperture, and point P is called as pole. Now all these terms were defined in the topics on spherical mirrors. It's the same terms used here, except that in case of spherical mirrors, the phenomenon was reflection, and in case of this spherical surfaces, it is refraction. Otherwise, the terms will have the same usual meaning. So this AB is aperture, P is called as pole of the spherical refracting surface, C is called as center of curvature, and then the distance between pole and center of curvature is called as radius of curvature, and symbol for that is capital R. Similarly, the imaginary line passing through center of curvature and the pole is called as principal axis. Remember these terms. Now here are some examples of spherical refracting surfaces. One example is the lens what is used in cameras, and there are many kinds of lenses given here. We will see what these are in the next lecture. For now, understand that examples of spherical refracting surfaces are lenses. Even here, we have sign convention. Recall that we had sign convention in case of spherical mirrors also. The same conventions are used here also, except for the fact that in case of mirrors, it was reflection, and here it is refraction. So, as seen in case of spherical mirrors, the first sign convention is that the distances are measured from pole of the refracting surface along the principal axis. So, pole becomes a reference point. Second point is, as seen in case of spherical mirrors, distances measured in the direction of incident ray is taken as positive, and distances measured in the direction opposite to that of incident ray are taken as negative. So, if light moves, say, from left to right, suppose if we move along the light itself, in that case the distance becomes positive, and suppose if we move against the light, in this case it becomes negative. So this is the second sign convention. Third one is heights above the principal axis is taken as positive, and heights below is taken as negative. So the conventions what was used earlier in case of spherical mirrors is the same points here also. In this case, let's assume that suppose somewhere here an object is placed, or we take a case where we'll have a convex surface. So think of a case like this where we have an object placed, for example at this point an object is placed. Now this would be its pole. If light falls from here to here, let's assume that this medium is a rarer medium and this is the denser medium. Now center of curvature of this, because this is part of sphere, so center of curvature for this spherical surface is somewhere here. We will call this as C. If we draw normal from this point C to the point of intersection, then since light is moving from rarer to denser medium, light ray would bend towards normal. So instead of going like this, light ray would bend towards normal. So the image is obtained somewhere here. So this is the point where image is obtained. Now in this case, just use sign conventions. In this case PO. So PO means distance between the object and the pole, which is PO. So by sign convention, since light is moving from left to right, we are starting from the pole and we are going towards O. So by sign convention, this PO would be minus U. Now PC, which is R, would be positive. So by sign convention, it would be positive R. So it becomes plus R, and PI in this case would be V. So this is the sign convention example of it. In case of a concave, say surface, what will happen is, suppose object is kept somewhere here and light falls on this surface. Now in this case, draw a normal at this point. If we draw normal at this point like this, then the light ray is moving from rarer to denser medium. So this light ray, instead of going like this, would bend towards normal. It will bend like this. If we draw it backwards, it appears as if light is coming somewhere from here. So this would be the image position. This would be I. So here, by sign convention, U, V and R, here all of this will be negative. So this is the sign convention. We take up a derivation here, which is an expression to find the relationship between refractive indices as well as U, V and then R. Now this derivation is true for any kind of spherical surface. We'll do it in case of a convex spherical surface, but whatever is done here, the same thing could be used even for concave spherical surface also. Let's assume that the medium here is a rarer medium and this is a denser medium. Now this would be its pole. Somewhere here an object is placed. Let its refractive index be n suffix r and this be, or we'll call it as n suffix 1 and this is n suffix 2. Now imagine a ray of light falls from the object at this point. So let this point to be, at this point to be M, where the light ray is incident. Since light is moving between two different mediums, and if you draw normal, imagine this is point C, somewhere here is point C. So from point C, if we draw a normal, the angle made here, so angle made here is called as I. Now the light ray, since it is moving from rarer to denser medium, this light ray would bend towards normal. Therefore finally somewhere here image is formed. Now this angle here would be R. Now by sign convention, in this case PO is equal to minus U and then PI is equal to plus V and PC is equal to plus R. So this is the basic diagram. Now let us make some construction. Let's drop a perpendicular from the point M onto the principal axis. So this would be its perpendicular, we call as point N. Now let's define three angles. We'll call this as angle alpha, this as angle beta, this is angle beta, and this as angle, say, delta. So here we define three angles called as alpha, beta, and then delta, where alpha is the angle which the incident ray makes with the principal axis, beta is the angle which the normal makes with principal axis as given here, and delta is the angle which the refracted ray makes with the principal axis. So we define three angles here. Now applying or using Snell's law or applying Snell's law at the first boundary, then what we get is, we get n1 into sin I is equal to n2 into sin R. So this is the first expression, we call it as 1. Now our aim here is to get the relationship between u, v and r. So we need to express these parameters in terms of u, v and r. Now let's begin. Now consider triangle, say OMN. So from triangle OMN, it's something of this kind. This is point O, this is point N, this is point M. The angle here is alpha. In this case, tan alpha is equal to Mn by On. Now from triangle, say MNC, it's like this. From this triangle, this is point M, this is point N, this is point C. The angle here is beta. In this case, tan beta is equal to Mn by NC. This is O here. And we'll take the third triangle. We'll do it here only. So in triangle MNI, it's like this. So this is point N, this is point M, this is point I. Angle here is delta. So from this, if we find what is tan delta here is equal to Mn by Ni. So we have three relationship here. To understand that, I told you in earlier classes that the entire course on ray optics, the assumption is we consider only paraxial rays. So for paraxial, rays, it means that the light rays are very close to the principal axis. Now let's take a case where we have light ray which falls like this close to principal axis. And do remember I told you in the previous classes that we draw the light rays far away because we need to represent and show the diagrams. Otherwise, the assumption is the light rays are paraxial rays. So for paraxial rays, the angle alpha becomes very small. And also, if we draw normal here from this point, even beta becomes small, even r becomes small. So in that case, if we drop from here perpendicular, this point N goes to point P. So for paraxial rays, angles alpha, R, beta, delta and I, these would be small angles, and also the point N comes towards point P. So what I can do is, we can replace these angles by the approximations and also replace N in the denominator with P, because P is a reference point. So what I mean by that is, the paraxial rays, the angles are very small. So that would mean that sine I is same as I itself, because recall, for small angles, sine theta is almost same as theta itself, and then cos theta is almost 1, and then tan theta is same as theta itself. So with that logic, for small angles, sine I becomes I, and then sine R is almost same as R itself. And also tan alpha is almost same as alpha itself. Tan beta is almost same as beta itself. And then tan delta is almost same as delta itself. And also replace the points N with point C. Do it only in denominator, because anyway this will get cancelled. So that means that this term becomes alpha is equal to mn by replacing point N with point P. So it becomes PO, and this becomes beta is equal to mn by NC becomes PC, and from here we get delta is equal to mn by Pi, so that we get PO, PC and then Pi, which is in terms of U, R and then V. Now what we'll do is, from here, from this equation number 1, we can write N into I, or N1 into I is equal to N2 into R. But let us find what is I and R from this triangles. So from this triangle, say OCI, from triangle OCI, what we get is, we get something of this kind. This is point O, this is point C, this is point I, this was I, this is point M, sorry, this is point M. Okay, sorry, this is point, this triangle OCM. This is point M, okay, this is point M here. Angle here is alpha, this is beta. So you learned in high school that first triangle, what you get from here is, you can say I is equal to alpha plus beta, and we'll consider one more triangle which is MCI. So from triangle MCI, just read out here this triangle MCI. So what we get is, we have something like this. This is what we get. This is point M, this is point C, this is point I. The angle here was R, this was beta, this was delta. So from here what we get is, we get beta is equal to R plus delta, or R is equal to beta minus delta. So putting the value of I and R in this equation, where N1I is equal to N2 into R, and what we get here is, read this, N1 into I was alpha plus beta, that is equal to N2 into R from here was beta minus delta. So it is beta minus delta. Now let's bring the terms beta on one side. So N1, it becomes N1 and this becomes N2 to bring this side. So minus N2 into beta, that is equal to minus N2 into delta minus N1 into beta from here, no, alpha from here. So there's one term, N1 beta is already here, that's first term, and then this becomes N2 beta minus sign here. Now putting back the values, it is N1 minus N2 into beta was Mn by Pc, that is equal to minus of N2 into delta. Delta was Mn by Ni or Mn by Pi. This delta here, Mn by Pi. So Mn by Pi minus N1 into alpha, it's Mn by Po. So it is Mn by Po. Now from here, Mn gets cancelled. So what we get from here would be, it will be N1 minus N2 by 1 by R is equal to minus N2 into V, and this becomes plus N1 by U because PO is minus U, it becomes positive. If you flip the minus reverse sign, so take minus 1 outside here, this becomes N2 minus N1 1 by R or by R. So this becomes N2 by V minus N1 into U. So what I did here is I just multiplied this equation by minus sign. This is what I get. So this is the required equation, which is so N2 by V minus N1 by U is equal to N2 minus N1 by R. So this is the required expression. The term here, this term here is called as refracting power. It's called as refracting power. Now, even though we have derived this for a convex spherical surface, this equation is true for any kind of spherical surface. Second point is, whenever you're doing some numericals based on this formula, again use sign convention. Even if it is a convex surface also, use with sign convention, which means U becomes negative, V will be positive, and also R will be positive. Now one thing is how to remember the terms. Now what students do here is, most students would by heart the equation as given here, but they would always think that N1 is the first medium and N2 is the second medium's refractive index. That can be true in most cases, but this formula becomes confusing to remember when we do about virtual objects. So there it becomes confusing. So to avoid the problem, to make it more simpler, always think N1 as the light originating medium. So it is light originating medium, or you can think of this as direction of light ray. It means from where is light ray moving, and N2 is the other medium. Now this becomes clear if we take the derivation on lenses. Just for now, remember the fact that N1 is a medium, N1 is the refractive index of the medium where light is originating from, where light is starting from, and N2 is the other medium. As we saw earlier, the ratio n2 minus n1 by r, which is the term on the right hand side, this is called as refracting power. So to define it, we can say refracting power of a spherical surface is defined as the reciprocal of the reduced focal length. Let's not go into so much detail as to what does reduced focal length mean and all. For this class, understand that the term n2 minus n1 by r is called as refracting power. Now to understand what does a focal length mean, we have done in the previous classes also. To define focal length, we take parallel beam of light rays. So that would mean that u tends to infinity. So whenever u is very very far away, that is, the object is very very far away, then u becomes very large. For large distances of the object, the light rays would be parallel. And we know that the point where image is found becomes the focus point, and that would be V. So whenever u tends to infinity, V becomes F. That is the point where image is formed. Putting these parameters here, what we get would be n2 by F is equal to, because 1 by infinity would be a small number, we can neglect that, because what we have here is we have n1 by infinity, which is basically 0. It's equal to n2 minus n1 by r. Therefore from here, if we solve it, then F is equal to n2r by n2 minus n1. So this is called as the image focus, and by convention this would be its focal length also. Don't get confused with F is equal to r by 2. F is equal to r by 2 was the focal length only for spherical mirrors, because most students would tend to buy at this because this is simple to memorize, and they would think that this formula holds for every spherical surface. It isn't true. F is equal to r by 2 is only true for spherical mirrors. The form would change based on the elements also. It is different in case of a spherical refracting surface. The form would be different for lenses also. So F is equal to r by 2 is only for spherical mirrors. We'll take some numericals to understand the earlier concept. Example 1 says a spherical surface of radius 30 cm separates through transparent media. Media means it is plural for medium, called as A and B, with refractive indices 1.33 and 1.48 respectively. The medium A is on the convex side of the surface. There's a comma should be here. Where should a point object be placed in medium A so that the rays become parallel after refraction? So we have a spherical surface. Now question says the medium A is on the convex side. Now out of these two refractive indices, 1.33 is less than 1.48. The question says the medium A is on the convex side. We learned that for a mirror or for any spherical surface, this would be the convex shape. So the medium A is on the convex side. That would mean that medium A is on this side, and this should be medium B. A's refractive index is 1.33 and B's refractive index is 1.48. Now question says where should an object be placed in the medium A so that the rays become parallel after refraction? So it means that suppose somewhere here an object is placed and then this light ray say falls. The question says these light rays after refraction become parallel. So it goes like this. And a similar ray here also. It goes like this. They become parallel. So it would mean that these light rays would tend to infinity. So it basically means that here V tends to infinity. Question says find what is U. So we know the formula N2 by V minus N1 by U is equal to N2 minus N1 by R. So this is the required formula. In this case, N1, the object is placed in medium A. So as we saw earlier, N1 is the light originating medium. In this case, N1 is equal to 1.33, and then N2 in this case is the other medium whose refractive index is 1.48, and also R is given as 30 centimeter. It's a sphere basically here, so it's 30 centimeter. By sign convention, this would be the pole, and the spherical surface would have center of curvature to the right of point O. So somewhere here is center of curvature C. By sign convention, PC would be equal to 0.3 meter because it is given as 30 centimeter. Let's plug in the values. So 1.48 by V tends to infinity is equal to or minus N1 is 1.33 by U, that is equal to 1.48 minus 1.33 by 0.3. This would tend to 0. So what we get here is minus 1.33 by U is equal to 1.48 minus 1.33 would be 0.15. It will be 0.15 by 0.3. 0.15 by 0.3 would be 0.5. So from here, what we get would be U is equal to minus 1.33 by 0.5, that is equal to minus of 2.67 meter. The minus sign indicates that the object is placed in front of the convex side. So this is the required answer. Example 2 says a glass sphere of refractive index 1.5 has a diameter of 0.2 meter. A parallel beam is incident on the sphere. Where is it brought to focus by the sphere? So we'll first draw a sphere. So what is given here is we have a sphere here. Now this would be center of the sphere. Now what is given is this glass has a refractive index of 1.5 and nothing is given about the other medium. So we assume that this sphere is kept in air or placed in air. A parallel beam is incident on the sphere. Where is it brought to focus by the sphere? So what is given is light falling here, the parallel beam. So a parallel beam falls on this sphere. Question says where is it brought to focus? In this case, what you can do is you can assume that we can divide this sphere into two parts. We'll call this point as say point A, point B, point D, and point E. So we can assume that this sphere consists of two refracting surfaces. The surface ABC, which acts like a convex surface, and even the part AED also acts like a convex surface only. So you can imagine that this acts like two different spherical surfaces. One is ABD, other is AED. Now first and foremost, we should find out what happens to the image at the first part. So suppose if these light rays refract and the image is found somewhere here only in the sphere itself, then there's no need to do anything further beyond that. But think of a case where these light rays are tending to go. They're going like this, which means these light rays are tending to meet at a point beyond this surface AED. Now what will happen here is, if surface AED was not there, these light rays may go to a point. But because of surface AED, these light rays would further refract the surface AED also. So in this case, we may get two refractions. So first find out whether the image is formed within the sphere or is the light ray tending to go beyond the point E. To understand this, recall that the sphere radius is 0.2 meter. So the whole distance from here to here is given as 0.2 meter, which means C to B would be 0.1 meter and then C to E would be again 0.1 meter. So we'll first take the surface ABD. So consider the surface ABD. For the surface ABD, something of this kind. For the surface, we'll find what is V. So this is point A, this is point B, this is point D, and this is the principal axis. Now for the surface ABD, B is its pole. So the light rays falling are parallel. So light rays falling would be parallel for the surface. So for the first surface, or for the surface ABD, for this U is tending to infinity, and the center of this is somewhere here. So this will be point C. By sign convention, PC, which is R, here would be 0.1 meter because the diameter is 0.2 meter. And in this case, N1 would be 1 because light is starting originating from air. And N2 would be the refractive index of this glass sphere, and that is given as 1.5. So here N2 is equal to 1.5. So let's find what is V from this. Formula is N2 by V minus N1 by U is equal to N2 minus N1 by R. So here N2 is 1.5. So 1.5 by V minus this term would tend to 0 because U tends to infinity, that becomes 0. It is equal to 1.5 minus 1 by 0.1, that is equal to 0.5 by 0.1. So this is equal to, from here, if you cross multiply solve it, V is equal to 1.5 into 0.1 by 0.5. It's 1s are, 3s are, and 3 into 0.1 would be 0.3. Therefore, in this case V is equal to 0.3 meter. Now recall that for the surface ABD, B is the pole. So light rays from here are tending, they're trying to meet at a point. So they're meeting at a point which is at a distance of 0.3 meter from this thing. But recall, what is its, drop this part here. So we'll take somewhere here C. So distance between B to this point V, or the point image point, I just call as I dash, is 0.3 meter. But the distance between point B to point E here, point E was other part of the spherical surface. So for this point E, it is from B to E, it is 0.2 meter. So the light rays are going beyond the second surface, because of which the light rays would further refract here. So to draw it here, these light rays were tending to go towards a point. So these light rays were tending to go to a point like this, but because of refraction they bent further and the image is formed somewhere here. So this you call as I dash, this is I. So I dash is the point where image would have been formed if we had no surface AED, but because of surface AED the light refracts and the image is formed at the point I. We just draw the part AED separately. So for the part AED, like this, the light rays were tending to go, they're going like this and like this. So these light rays were going towards a point. So the point where they're trying to go, we call it as I dash. Basically from this point E, the distance was 0.1 meter. So it is 0.1 meter. But because of presence of surface AED, the light further refracts here. Finally, the image is formed somewhere here. It's formed like this because it further refracts. So this point I is the point where image actually formed. So we should find what this distance EI is. Now for the entire surface, for the entire sphere, the image is formed at point I only. Now the question is, for the surface AED, I is the image point. Now for the surface, where is the object is the question. The object cannot be at infinity because U being at infinite is the object, or object being very far away is for the surface ABD only. So for the surface AED, the object is not at infinity. Rather, the image which is formed at the point I dash. So this image formed here would act like a virtual object for I. So this is the concept of virtual object. We done in the first lecture only. We saw that for a real object, light rays would diverge, go away from it. That's a real object. But for virtual object, light rays would tend to converge. It is called as virtual object, as we saw in the first lecture. So in this case, I dash acts like a virtual object. Now in this question, we should find out what is EI. So here, to solve further, let's find what is N1 and what is N2. The refractive index of glass is 1.5. So here, we'll find out what is N1 and other things. N1 and N2. Now what many would think that in this case it's confusing also, because the object which is virtual and image are in the same side only. So as I told you earlier, we should always think of N1 as the light originating medium. So light is coming from the glass sphere. Therefore N1 in this case is 1.5. That's what N1 is. So don't learn N1 as the object medium because it becomes confusing in these cases. So think N1 as the light originating medium, and N2 would be the other medium, which in this case is air. So here N2 is equal to 1. And in this case PC, which is R, by sign convention would be minus 0.1 meter, because light is moving from left to right and the center somewhere here. They are going against light. So by sign convention, PC, which is R, is equal to minus 0.1 meter. Do remember that in case of optics, the numericals or the formulas are quite straightforward, but there is a high chance of getting it wrong if students are not careful with sign conventions. And here U would be plus this positive, which is plus 0.1 meter. That's because distance between E to I dash is 0.1 meter, and we should find what is V. So using the formula, we know that N2 by V minus N1 by U is equal to N2 minus N1 by R. Putting the values here, N2 is 1 by V minus N1 is 1.5 by U is 0.1, that is equal to 1 minus 1.5 by R is minus 0.1. So this would give us 1 by V is equal to 1 minus 1.5 is 0.5, minus 0.5. So minus 0.5 by minus 0.1 would be 5, and this becomes plus 1.5 point would be 15. It becomes by 15. So from here 1 by V is equal to 20. Therefore V is equal to 1 by 20, which is 0.05, and the units of U, V and R was in meter. This also becomes in meter. It becomes 0.5 meter, which is expected because the light rays are converging to a distance of 0.1 meter. So the light rays, because of refraction, with further bend. So the image is formed at distance which is less than 0.1, which in this case is 0.05 meter. Thank you.